Hey, what's up, guys? This is Sheng here. It's been a while, yeah, but I'm back. So I'll try to catch up with all the weekly contest problems. So today, 1,976 number of ways to arrive at destinations, right? So for this one, you're given like a city that consists of n intersections, numbered from n to n 0 to n minus 1. And then we have a bunch of rows between some nodes, right? And then you're given like an integer with integer of n and 2D integer array rows, where the rows basically you have a u and v and time, right? So basically this is like a weighted graph problem, right? And also as you guys can see, um, we want to get the shortest amount of time, right? Basically, this is obviously a shortest path problem, but the difference for this problem is that we want to return the number of ways that you can travel from the start to the end, which is the node 0 to node n minus 1. Okay, and remember in the shortest amount of time. Okay, right? So basically, we're trying to get the number of ways that we can reach the destination in the shortest path. Okay. So for example, right, we have, so this is the start, right? And this is the end, right? 6 is the end. So here we how many ways? We have 4, right? So we have 4 because which 4? So we have 7 because obviously, um, or apparently the shortest path is 7, right? We can simply just get the answer by watching the graph here. Basically, we have this one, right, and this one, and we have uh, this one, right, and then this one, right. So basically, that's the 4 path that can give us the shortest path. Okay, and yeah, and so here are the constraints, right. So for this problem, since we are going to get the shortest path, right, or shortest path in this graph, and we'll definitely be using Digestion algorithm one way or the other, right? Because with Digestion algorithm, we can just simply get the shortest path between between the start between 0 to any of the node, right? But the difficulty for this one is that how can we, while getting the shortest path, how can we get the number of ways, right? Because we want to make sure the ways we're counting is the shortest path. It's part of the shortest path, right? And actually, so to solve this problem, you guys need to understand. So the nature of the Dijkstra is what is improve the distance between two nodes, right? And so let's say, for example, right, we have let's say we have this example here, right? This is start. We have this kind of node, right? And then we have this. Okay, this is a node. This is one. And then we have this one, right? And then here's the end. Okay, for example, this is a start, and this is the end. And the weight we have is 2, 2, 3, 3, and then 1, 1, 1, 1. And then here we have 2, 2, 2, and 1, 1, 1, right? So by looking at this one, right? So the shortest path from S to this one is what? It's 3, right? Not 4. Basically, now we have what? How many ways we have? How many ways we have so that we can travel from the start to this node with the shortest path? It's 2, right? It's 2 because we have this path and we have this path. Not this 2, right? These two paths are not the shortest path. And then here on the second part here, they are actually all the 3 parts they're the same, right? So what do we have? We have 2 times 3 equals to 6, right? That's basically the answer for this graph. And so the way we are solving this problem is that we're going to piggyback on the Digestion algorithm, right? The only difference is that while, remember, so we're trying to improve the distance, right, between this S to this current node, right? And every time when we update, okay, so when we find a better path, or we find a shorter path for this node, right, which means we're going to update the distance array for this node, we will basically reset the path, right, or the weight for this node, which means that besides this distance array here, right, we'll also be creating like another arrays here, which is the weights for each of the node. Okay, because every time so remember, so in Digestion algorithm, right, whenever we're trying to update this distance, right, it means that we find a better path, or we find a shorter path, right, or a path with like with a smaller weight, right. That's when we need to update this distance, right. And then, but in this case, other than the 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 shorter distance, there could be also like other path that will give us the same weight, or the same weight, right? For example, this one. In this case, what do? We accumulate that. We accumulate that part, that path who can give us the same weight as the current one, right? And then in the end, we'll get the answers we need. Basically, will be the weights of -1. That will be our final answer, because as you guys can see, right? So let's say for this node, right? For this node, let's say we process this path first. Okay, we process this path first, and then the distance for this one will be 4, right? The distance will be 4 for this one, and then the weights will also be 1. And then let's say the next time we process this path, since this path give us the same distance, right? And then this one will become 2 to what? The weights will become 2 to 2 in this case, right? Because we find the same path. But now let's say if we start processing this path, okay, now we see, okay, this path will give us a better answer, right? Which means we need to update this distance. Okay, so whenever we update this distance from 3 to what? 3 from 4 to 3, that's when we also need to reset this weight, because with the current 2, it doesn't mean anything, because we find a better path. It means that the weights we're calculating are not part of the shortest path, which means this one needs to go back to 1, right? And then here we have this another one. This is 2, because right. So that's how we calculate this distance and weights. And in the end, we simply return this one. Yeah, so let's start coding, and I'll explain a little bit more along the way. So first, the Digestion, right? So the Digestion, I think most of you already know how to code the Digestion algorithm. So I'll just quickly implement that. So we have a U and a V and what, and so in this problem we have time, right, instead of weight. So I'm just gonna use the T here in rows, right? So first we create a graph of U dot append. We have V and W. Sorry, not T. Okay, and then we have a graph. Since it's bidirectional, right? Append of U dot T. Okay. Now we have a distance in this case, right? And well, let's try to accommodate with the terminology for this problem. Instead of distance, let's call it times. Okay. So the times is stores the current shortest time from node 0 to the current node. Okay. And then obviously the times 0 will be 0. Okay, right? and then we have weights gonna be 0 times n, right? So for weights 0, it's gonna be 1 because we need this base case, right? And then the priority queue, right? For stack control, we need the priority queue. So this one we have 0 and 0. Okay. So basically, this one is what? It's the time. It's the shortest time, right? And the node, right? And the city, actually the city. Okay. And the while priority queue. So let's say we have old time. Okay, and we have u equals to heap pop of priority queue, right? And then for all the neighbors, w in graph of u. Okay, we have a new time equals to old time plus plus time. Okay, so the Digestion algorithm is like this. So if the new t is smaller than the current times of v, right? That's when we're gonna update. We're gonna heap push this new entry, right, to the priority queue, which is gonna be the new t and the v, right? And then we also need to update the times of the v equals to the new t, right? So that's basically the Digestion algorithm. But for this problem, we also need to update this weights, right? Like I said, whenever we find a better path, right? So we reset the weights of the current node to the weights of u, right? Because let's say for example, this is the current node, this is a v, right? So we have a many path can lead to here, right? So we have this u1, u2, and u3, right? So let's say this one can give us like this one can give us like weight of 5, right? And then for this one we have what we have like the weight is going to be the weight for this path is, let's say it's 4, right? And then we find a better path from this u2, right? For this one, the ways to get to u2 is like what is 3, right? Then it means that we're gonna completely discard this path and we're gonna start using this one, because this one, no matter how many ways we can get to the u2, will be the ways for the current v node, right? That's why we're gonna do this update. And then the next thing is that, else if, right? Like I said, there's another scenario. If the new w is equal, right, to the times of v, right? That's when we need to accumulate. You're gonna accumulate this one to the current u, right? So that's another scenario. And then that's it, right? So that's how we update the weights here. And then we just need to do the modular in the end. So it's going to be the weights of -1 and divide it, do a modular with mod. Okay. So I think that's it, right? And if I run the code, default dict AULT. Okay. Yep. So that's it, right? Yeah. I mean, so for the time complexity, I mean, I think for the Digestion algorithm with the priority queue, the time complexity would be the v plus, I think it's e times log v, right? Yeah. So for this problem, we have what? So we have n, that's the number of nodes, right? And then we have this n square of edges, right? So which means this one is going to be n plus what? Edge is going to be a n square log n, right? Yeah, so I think that's the time complexity for this one. Yeah, so I think that's it. I mean, I think this one is a very I think it's a good problem in terms of the Digestion algorithm. It helps you to know a little bit more, right, deeper about the nature of the Digestion, right? So basically, you need to understand why when are we updating this times array here, and why we're updating it, and when we update it, and what's going to happen? It means that we find a better path, right, from the start node to the current node, right? Then it means that we need to recalculate the ways to reach the current path, the current node, right? That's how we are. That's why we reset here, and then this one is for the for multiple paths can lead to the same, can give us the same shortest time, right? Yeah, I think that's it for this one. I hope you guys like the video, and thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.